Okay, ladies and gents, let's get started on this chemistry paper 2. First question is about ion identification. Flame tests, you need to be able to describe how to do them, and in this case you need to know the colours of the flames. It's straight there in the revision guide. There's only about 4 or 5 that you need to know off the top of your head. So in this case, sodium, yellow, green flame would be copper. Obviously you're allowed to put the copper 2+ ion in there. There's other ones that can do the same result. For example, there in the mark scheme, it allows barium. You don't need to know that. For part 3, some fireworks contain a mixture. Why is that difficult? This is where we started losing some of our first marks. You don't get rainbow flames by adding different colours, and that's one of the things you guys might remember when you've done one colour, you've done another colour. When you start, what happens when we mix a couple of them together? It doesn't. You usually just see one. So one colour is hidden or masked behind another. And in 1.4, this one's quite well done because you're pretty good at interpreting these diagrams. We're looking at what's in the mixture. It's all down to the patterns. So what we should be looking for is the lithium pattern that you can see going down through the same marks, and also the sodium pattern right above it. You can see it's got the same marks in it as well. So you'd need to tick 2 boxes, lithium and sodium. You did well on that one generally. For 1.5 and 6, these ones, yeah, a lot of people lost marks on these ones. So the clue here for this one is when we see a cream precipitate form. There's a lot of white precipitates when we're looking at ion tests, but the cream precipitate forms when we're looking at halides, things the ions from group 7, the halogens, and the order goes white, then cream, then yellow, and that's for chlorine, bromine and iodine. So cream's right in the middle. It's the bromine that should be reminding us of. The bit that people lost marks on as well, if they got that right, the bromine is the thing that's doing it, but it's an ion, so you have to call it a bromide. Now you're probably going to look up and start arguing with me about this one, but they're being very, very specific on this. See, it says ignore bromine. So it's the bromide ion. 1.6, one of the other tests that people don't like, again, like I said before, a lot of the results are white precipitates. So if you're not sure on these questions, for the result, write down, you'll see a white precipitate. That's one of the marks that we'll get here. The other ones are for adding a particular acid. So you could have gone for hydrochloric acid and you could have gone for nitric acid. Why would you not be allowed sulfuric acid? Because sulfuric acid might react with an impurity to put a sulfate ion in there and to contaminate your test. Okay. Nitric acid is usually a pretty safe one to go for because hydrochloric acid you can't use for testing for halides. So again, 2 things there. If in doubt, put it's going to be a white precipitate and add nitric acid. The hardest bit to remember then is you allowed barium chloride or barium nitrate as the other reagent that's required for this test. A lot of people put barium sulfate, but the problem is that's what's being produced at the end. Question 2 then. This is quite interesting because it links into the fuel that we use for the stoves in DAV, and that makes a lot of the people that went on that start talking about it. What's the name given to a useful product such as methylated spirit? That is a bit of a awkward way of phrasing it, but what they're asking you for is the answer formulation. That was where we had described it as being a particular recipe or formula that's used for a product, so that it's got the right ratio of ingredients, whether it's paint, whether it's pills, or in this case the methylated spirits. For calculating the percentage by mass, most people were pretty good at this, and if you got it wrong, it's quite often because you didn't add a total mass up. So if we have a look at the mark scheme on the right here, the 23.3 comes from the methanol, which is what we're trying to find the percentage of, and then the numbers at the bottom are the total mass of everything added together. So when you add all those up, it's 293.3. So it was 23.3 out of 293.3. Obviously times it by 100. That's 7.9%, but obviously we've allowed anything that's rounded correctly. I hope you didn't put as many decimal places as that in, because that's a bit ridiculous, isn't it? For 2.3, why pyridine and methyl violet are added? Yeah, there's a couple of people saying that it would make it more enticing to drink, but it's exactly the opposite. We're going to try and stop people from consuming or drinking it. because it's making it a very unpleasant smell, and the purple colour gives you a very clear indication that it's not water, it's not something else that's nice. Let's have a look at the next one. Suggest one use of methylated spirits. Most people that went for it put down a fuel solvent. They were pretty common because we've actually burnt that in little spirit burners in our lessons. For 2.5, not as universally good at this, and I think that's possibly because you didn't really spot what the question was asking you for. So the first thing is that when you're making ethanol from the sugar solution, it's kind of a stealth biology question. We have covered it in chemistry though. So the process is fermentation. There's your first mark. So fermentation is where you add yeast. That's your microorganism which carries out the process. That's your second mark. Third mark is for some of the conditions. So it's anaerobic, so you might remember seeing cotton wool being put in the top to stop that getting out, or even a warm temperature. So we're looking anywhere where enzymes are going to work effectively. So I'd expect you to say something like 35 or 40 degrees Celsius, and the maximum range that they're allowing here is 45 degrees, obviously, because at that point proteins would be denaturing and oops, we're suddenly into the biology territory. 2.6. For naming the gas produced when sodium is added to ethanol. So this bit's quite a small bit of the curriculum. We did show this one happening. It's hydrogen. They could have been slightly harder on this one, where they could have asked you to name the product of it, which in this case would be sodium ethoxide. Which is just one of those little random facts that I remember telling you that they could well ask you about this reaction. They could ask you to name this. What they were slightly awkward at was they said what type of substance reacts with methanol to produce methanoic acid. And that's the reason that's quite awkward is it's asking you about an oxidizing agent, about something that gives oxygen to it. But they've said ignore oxygen. So when we've talked about it most times in class and we're talking about alcohol being left out, wine bottles being left out, we've talked about oxygen reacting from the atmosphere. We did mention a particular type of breathalyzer which used a permanganate crystal to change colour. But this 2.8 is the very last question in this. It's supposed to be the hardest one, and that's why it's not really a problem that a lot of people lost that mark, because it's meant to be a tough question. Right, question 3. So, Haber process is probably something you're sick to death of, but it is something that you should have a good understanding of, because it's got so many good examples of principles that if they're not asking about the Haber process, they can ask you something very, very similar about a different process. And if you can apply the principles here, it's going to be really useful. So, skills here, we should know that ammonia is made out of nitrogen and hydrogen. They've said nitrogen's going in, so gas X must be the hydrogen. 3.2. Some people lost marks here because they just put numbers, right? It's 450 degrees Celsius and it's 200 atmospheres of pressure. Now, if you gave alternative units that were in the right answer, that'd be fine. If you did it in Fahrenheit or if you did it in pascals of pressure, that'd be okay. But you were only getting 1 mark if you didn't include the units. Some people just got them mixed up the other way around, which, just tells me you've read the information, you remember what's going on, you just got them confused. Long term, that's not a worry for me. Suggest why ammonia condenses but the other gases don't. A good chunk of people said that ammonia has got the higher boiling point, so it's harder for it to stay evaporated. And a lot of people that got it wrong just said it the other way around. They said that ammonia has a lower boiling point. I can see where you came from there, and hopefully when you stop and think about it, you'll just do that little, oh yeah, all right then, and then realise why that was the wrong one. 3.4, we had some good ones for this one. So first of all, it's asking you a very specific point. It's saying, here's the atmosphere that we think was originally there, and here's the atmosphere today. Now, it doesn't ask you where this came from. So some people started off, like we did in the lesson, talking about volcanoes and the fact what came out of volcanoes and all that sort of stuff. And it's a lovely bit of the story, but it didn't actually score you any marks in the question. Some other people remembered some parts of the lessons that we did as well, where we had something cooling, condensing and forming the oceans. That wasn't carbon dioxide, unfortunately. Obviously it's water vapour that cooled and condensed and formed the oceans. So let's start having a little look at what we need to actually get the 6 marks. The most important thing is that it's a clear, logical process. Okay, so ideally we'd be starting talking about the original atmosphere and how one gas changed and affected to where it's at today's amount. So for example, if we started with carbon dioxide, you'd need to describe how carbon dioxide could change to be from 96% to less than 1%. So we'd be looking at primarily the first answer. You'd say photosynthesis. Plants take in carbon dioxide as part of the photosynthesis reaction. The bonus point in saying that is you could also say that then that gives out oxygen as well as a byproduct. This would explain the decrease in carbon dioxide and the increase in oxygen. So that little bit on its own is probably worth 4 marks, because what we've done is we've said that carbon dioxide decreased and oxygen increased. And as stupid as that sounds, there's a lot of people that didn't actually mention that bit. When we look at the level 2 answer, we've got some relevant points in there talking about photosynthesis, some logical thinking describing how the changes happened, but the account is not fully clear because there are a lot of other factors that affect it locked up here. Okay, so if we're looking at 6 marks, what we're looking at trying to do is then expand it. So we could say things like some of the carbon dioxide was absorbed into the oceans. Because of that, some of that carbon dioxide in the oceans was available for the creation of things like shells, which could have then formed things like sedimentary rocks or sediments and trapped carbon dioxide there. And some of the marine creatures, the plants, the algae, the animals that have been around, they could also have died and formed fossils and been another way that carbon dioxide was trapped. So the top end answers, you'd be giving me a range of places where carbon dioxide could be absorbed. You only really need to talk about oxygen in the one place because oxygen is pretty much just down to the life and the photosynthesis. So 3.5, most popular incorrect answer, people were saying because no one was there. Okay, and unfortunately for you, there is this chunk here over it that says ignore there was no one there. Okay. Some people were getting marks for saying it's 4.6 billion years ago, which means there's limited or no evidence, because even if it was in rocks, even rocks that are that old have been destroyed, and that's what we're talking about. The fact that anything that was there as evidence might well have been destroyed or might be really difficult to find. So it's very difficult to prove something with very limited or no evidence. That's why we're in the start of the question, we're looking at Venus. Okay. Question 4 about chromatography. The mistakes people got that weren't mistakes, they mentioned about a lid. It's just a different way of holding up the piece of paper. We quite often used a stick of wood. The lid isn't a problem. Okay, so what is a problem is the starting line being drawn in ink, because then you might have the ink then running up the chromatography as well and interfering with the results. And the other thing is that in the question it says that they're insoluble in water, but they've used water as a solvent. So the problem was they've used water as a solvent, which means none of the inks are going to move because they won't dissolve in it. Okay. For 4.2, a lot of people did really good conclusions for this, and it's a similar thing to what we've seen before in these sort of questions. A is a single colour, B is a single colour, C is a mixture of 2 colours. The mixture in C does not contain any of the same dyes or colours that are in A or B. Okay, well, most people got a combination of those. Just be careful, you won't get the information saying, the marks saying A is only 1 and B is only 1, because that's counting as the same point. Okay. Cheeky one here. Normally, to work out an RF, we're looking at the distance that something's travelled. So, for example, A, we have this distance here between the line and where it's gone to. And then we divide it by the total distance the solvent has moved. So let's say the solvent reached up here, we'd have a bigger number, and we'd have a number between 0 and 1. 0, the solvent, the ink didn't move. 1, it moved all the way to the top. What they did is they asked you to actually work backwards. They've given you the RF and they've given how much it moves. They want to work out how much the solvent has moved. So you'd set it out the writing with a missing variable with X in, and then you'd have to rearrange it. When you do, you should get a sensible distance. The solvent should have moved more than the ink that's moved, so it's 4.9 centimetres. Right, question 5. Quite a lot of the time when you see an equation like this, and it's got the stake symbols included, there's usually a marking for something like that. So, first of all, sodium thiosulfate there, that's one of the chemicals in the required practical. So what they're talking about here is something that you need to know. Remember, the required practicals, whether it's biology, chemistry or physics, are always going to be a large chunk of what's on your test. So make sure that you know these inside and out. I'm talking things like how to do the method step by step, but also things like independent, dependent control variables that might affect the investigation, and also things like how you might improve accuracy, reliability, why something might be valid or not. They're pretty important bits to go through. So for this one, 5.1, why it becomes cloudy, it's all about this. So if you said that it produces sulfur, there's your first mark, and the reason that matters, sulfur is a solid, that would get you the mark. The proper word we use for that is a precipitate. So you'll remember seeing this when you had a conical flask and you gave it a little swirl, and eventually the black mark underneath it was no longer visible because there was that much sulfur blocking the way. It went really cloudy. Okay. Part 2 is explaining how to do that. Now the first thing to do, highlight that first bit, it's planning an investigation, this question. Some people went on to talk about collision theory and it was lovely, you had some nice ideas about it, it had nothing to do with the question. Okay? So, nice method over here. The more like this method it is, the more likely it is to be a logically sequenced investigation that produces valid results. If you're not on 6 marks, quite a lot of the time, it's because of this. Okay? You might have described the investigation but not described how you're going to keep it a fair test. So keep that in mind as we're going through it. Okay? So here's the first point you could have got that mark. Measure an indicated volume of sodium thiosulfate. You could have said 25 millilitres. Fine. You could have said 50. I don't care. As long as you've given me a specific amount that you could then repeat each time. That's going to give you some valid results. Put it in your conical flask. Add in a measured volume of hydrochloric acid, 5 millilitres, 10 millilitres. We don't really care in this case as long as you're allowing us to repeat the same amount each time. Some way of measuring the end result, so it could be a black cross, it could be a light sensor. Some enterprising people also came up with using a gas syringe. Aren't you clever? Very nice. Give it a nice little swirl so that you can allow the reactants to mix. It'd be unfair to swirl once but not swirl all the others. And you're starting the stop clock as soon as the 2 reactants are mixed together. You're going to stop the stop clock when you can't see the cross or when the light transmission can be logged over time. When you get to 50 centimetres cubed of gas, whatever it is, as long as you say what it is. Repeat it so that you can calculate a mean, which helps you create a more reliable result. And then another bit which some people forget, this bit. You've described how to do the investigation. Oh, maybe you didn't put in your controls or something like that. But then you didn't say that you were going to repeat it at different concentrations, for example, by having a more dilute solution. You didn't even have to explain how you were going to do it. You could have just said, I'm going to repeat it for these different concentrations. You could have said 1 molar, 2 molar, 3 molar, or you could have said a concentrated, a weak, medium and strongly concentrated solution. It didn't really matter as long as you were giving us the rough idea. Okay? Right, question 6. So polyesters are produced when monomers join together. We're looking for the small molecule that's lost. Remind you of the lesson. We talked about polyesters, we talked about polynucleotides, we talk about polysaccharides, and each time they were condensation, polymerization, because they made the polymer and water, which is where you're supposed to know that from. Okay. On this one, completing the structure. First thing, that's the H3 we'd want above this, and notice the bond is to the C. If you did a bond to the hydrogen, that's why you lost that mark. Cheeky. Okay. You'd have a hydrogen, and a hydrogen, completing the other 3 points of the 4 that you'd need to draw in. There's your first mark. You'd lose the double bond in the middle. You've broken that. You've done your lunch lady arms, split them out to the side, so we've got just one bond in the middle. There's a second chance for you to get your marks. And then the third one, you'd be putting the N, which started off over at the left, next to the brackets down here, a la the picture over here on the right hand side. Okay. For part 3, The key to this question is asking why it's more sustainable. So if you just said that mixing them together makes it wear out more slowly, you've not gone the full distance. Okay, so what are we looking for? When we're talking about sustainability, think about the starting materials. Wool is renewable, polypropylene is non-renewable. Okay, you can talk about the sources where they come from. Now, a wool carpet, although it's renewable, needs replacing more often, which then means that you need more land to grow wool, for the sheep to live on to then produce the wool, which you then make the carpets from. So that could be food land, which we don't want to take up all our land for sheep for carpets because it's just getting into a weird world there. So a blend would give you a good balance. It's going to be more resistant, it's going to last longer, it's going to mean that you make your finite resources last longer, but it's also going to mean that that it's going to be more sustainable than just using the hardware in polymer. Okay. Now this question here doesn't say sustainability. A lot of people talked about sustainability, but the question here is talking about suitability, how good it is for the job that we're looking at. So in this case here, the marks vary a little bit by the detail you need to go into. Okay, so for some of the things it's nice and easy. If you said that it's got a polyester, for example, has got a higher melting point and better flame resistance, then they're two good points to say straight up as it is, because the examiner's allowing you that. That's pretty straightforward. You know, if you're fighting fires, having a high melting point and being flame resistant is going to be good. What you're not getting credit for is just listing that a high water absorption or a high density or a low density is good. What we're looking for there is an explanation for why you've chosen those points. So, some people said that a high water absorption is good because it means it's less likely to ignite or set on fire. Some people said high water absorption is bad because it would make your clothes heavier. I'll give you that, but so you've explained it. Same thing with density. A high density could be a bad thing because it's heavy, and it's that little explanation that's going to get you that mark, which maybe you didn't. And last of all, you need a justification, you need a conclusion. So your choice, which one is best and why, because look at that first word, it's an evaluate question. So if you only got 3, that might well be why. Okay? Aren't we racing through? Question 7 then. Carbon monoxide produced in an engine. Okay, so what should flash up in your mind there is carbon monoxide is about incomplete combustion. There's your first mark. And then the explanation, we only get incomplete combustion when there's insufficient oxygen around. For 7.2, tells you it's not something that's possibly in your revision guide or in your lessons. But it's within your realm to hypothesize, so have a little think about why this might be. So it's why the maximum allowed percentage of carbon dioxide is decreased. And that's like a government decision. So we allowed, let's say, 50 arbitrary units in the 70s, and now we're only allowing 10. So then it's, well, why would the government legislate against that? So a lot of people know carbon monoxide is toxic. That's quite commonly a mark that people got. You can't just say it's bad for the environment, but you might say that, like, you know, people are concerned about it, so then the government then legislates against it. It might be that people are concerned about it, so it's one of their preferences when buying a car. So more modern cars are advertised on being more fuel efficient and greener for the environment, so that could be a good selling point for it. So you could sell it based on the improved engine technology. And also, I mean, they're not a new thing, but we didn't used to have catalytic converters and now we do, so it's another bit of knowledge that you could put in there. 7.3 then. This is a different thing. We're not talking about carbon monoxide anymore. That's where some people made a mistake here. We're talking about unburnt hydrocarbons. This is a problem, particularly in things like diesel engines, I think. And it's another one of the specific things about pollutants in the atmosphere that we need to know about. So any pollutant in the atmosphere affects how we breathe, so feel free to mention stuff like breathing difficulties and asthma. Now it says health problems, right? These aren't lethal. It's not like a car drives past and people drop dead. So you might feel aggrieved if you didn't get a mark for that. Tough. The other one that it can reduce is global dimming. So any particulate matter that gets into the atmosphere can block some of the incident energy from the sun, which can be quite nice because it can actually reduce the impact of some of the climate change that's going on. But obviously some of that particulate stuff is bad. It can form things like smog, which can be really bad for people breathing and staying alive. It's not really something we suffer from in the UK. Maybe more China. We used to have smog, but we started clearing out our atmosphere. 7.4 then. So first thing, the nitrogen is coming from the atmosphere, and a lot of people weren't really mentioning that. So it's nitrogen reacting with oxygen. The bit which a lot of people didn't get as a second mark, if you got 1 mark, it's at a really high temperature. Nitrogen, 78% of the atmosphere, doesn't really do much. It takes like lightning strikes, it takes a huge amount of energy. For 7.5, a lot of people got this wrong because they put just N as a gas. Now, when you have a simple gas structure like oxygen, chlorine, hydrogen, nitrogen, it's always N2. It's always O2. It's always H2. It's always Cl2 or Br2. So it's N2. There's your first mark. Okay? And then, however you balanced it, otherwise you weren't getting a mark unless you actually had that as a starting jump-off point. And then you'd know that there's going to be a 2 for the NO2 and 2 for the O2. 7.6 then. When we're looking about catalytic converters, you need to know what they're doing. So a catalytic converter is converting things like nitrogen oxides into nitrogen and oxygen. What problem would nitrogen oxides have caused? They would dissolve in clouds and they'd form nitric acid, which could form acid rain. It could have also caused breathing problems, which is where a couple of your answers on the right hand side go. What else do catalytic converters do? They take toxic, poisonous carbon monoxide and convert it into carbon dioxide. So 2 points here. It reduces carbon monoxide, which obviously is a good thing because that's toxic, but it increases the amount of carbon dioxide coming out of the car. And a lot of people said it reduces carbon dioxide. No, that's not the point of it. Carbon dioxide is actually safer than carbon monoxide. And there's a final point there that you could have mentioned. Global dimming or smog is from the unburnt fuel, the unburnt hydrocarbons we mentioned earlier, and catalytic converters help to burn those off. So, an answer that could have come up several times. This one links back into part of your stuff from the unit, the paper 1 stuff. So, transition metals, one of the things you need to know about those, they are what make good catalysts. It's catalyst, we're thinking transition metals. There we go, that's the tick box answer. Question 8. Right, why the conical flask is losing mass in this question. So again, this is a required practical thing, investigating how to measure the rate of reaction. The thing that we're looking out for here is it's a carbonate with hydrochloric acid. So the carbonate is going to produce carbon dioxide. So the point that you're getting here is a gas is produced and that gas can escape. Okay. Carbon dioxide is a good one to name, but if you said anything like hydrogen or any others, you're not scoring the mark. Okay, you can't just make up a random gas. Here are some points to plot. There's the graph where most of you plotted it absolutely fine. I was kind of mean here. A lot of people plotted the points accurately. A couple of people just misread it and maybe plotted 1 point incorrectly. A lot of people lost marks for line of best fit. I want a single line. It's a smooth curve. Maybe it's got a straight bit to it. Maybe it's a straight line drawn with a ruler. It's definitely not dot to dot. And it's definitely not got tram lining where you've got multiple lines visible. Okay? Now I think some examiners will allow it at GCSE, but it's just poor form looking ahead to when you actually, are going to get properly punished and penalised for drawing poor graphs later on. Whether you do whatever subjects in A-levels, if you're drawing a graph, it's a single smooth line. For 8.3, this is where you're supposed to draw a tangent. No tangent, no marks. Okay, so what a tangent is where you, when it says determine the rate of the reaction at 50 degrees C, when you see that command, you're going to go to 50 degrees Celsius, go up to that, and you're going to draw a line which hits the curve at that exact point. Okay, so when you're looking at calculating a rate, if it says between, you're doing an average rate, you can find the difference like a lot of you did. So in that case, if we did say between a certain time, say between 0 and 100, you could do the change in 100 seconds, which is 0.98, and divide it by the 100 seconds and get a rate. That'd be a straight line. That'd be that doesn't apply to the curve. So in this case, when it says the rate of reaction at 50 degrees Celsius, the at tells you it's a tangent that we're going to be doing. It wants to know the gradient at that very specific point. So it's straight line across. It should have an even sort of angle at both of those, judging it by eye, which means that your final answer might have a slightly different answer, but it won't be the same as if you just did a straight average of the rate of reaction between the 2 points. So we get the mark for drawing the tangent. You get a mark for very clearly showing you working out how you get some values on the x and the y axis. So once you've got your tangent, you need to know the height change in the y-axis and the horizontal distance change in the x-axis. You can then work out a rate by doing the change in the y-axis and divide it by the change in the x-axis. And the marks at the question says we need to round it to 2 significant figures. So whatever answer you get, round it to 2 significant figures, and that's where your final mark's coming from. And question 9.1 then. It's a bit of a funny one to put in the chemistry on this, but what type of substance acts as a catalyst in the body for digestion? Oh, you should be kicking yourself if you didn't put an enzyme in there. I mean, like, that's just straight biology, isn't it? For 9.2. In this case, when you see moles, don't big out, don't panic. You don't even need to know the 6.02 times 10 to the 23. What the equation here is showing you that 1 mole of this will need 2 moles of that. So 10 moles of that would need 20 moles of that. 1,000 would need 2,000 of this. So how many have we got? We've got 4 times 10 to the 3 of the hydrogen. Okay, so if we've got 4 of that, we must have half this. So it'd be 2 times 10 to the 3. It'd be this one. And I'd forgive you if you tick the 8, because you might have just said, oh, misread it, thought it was 4 of the carbon monoxide and doubled it to get this one. But that's still wrong. 9.3. Pretty well answered on this one. The forward reaction is exothermic. What would happen if you had a higher temperature? You'd have a smaller yield, there'd be less methanol made. The reason for that is that it's the Le Chatelier's principle, so it's going to favour the opposite, it's going to favour the endothermic reaction. And again, when you're doing these things about Le Chatelier's principle, it's pretty much 50-50. So either the yield's going to increase or it's going to decrease. And if you're not sure, pick one. You could also say, it favours the forward reaction or the reverse action for the second mark. And again, it's 50-50. If you're not sure, have a guess. Right, 9.4. This covers 2 different areas, and a lot of people maybe covered one, but not the other. So let's have a look at it. Pressure of 100 atmospheres instead of atmospheric pressure. That's going to answer the first bit where we're looking at the greater yield. Okay, so if we have a quick look at the equation, if we increase the pressure, over here we've got 1 of this, and we've got 2 of that, and the 1 and the 2 added together, that's 3 on the left. 3 moles of that. And over here we've just got 1 mole of the product being created. So that's a 3 to 1. If we increase the pressure, we're going to go from where there's lots of the gas to where there's less of it. So the first thing we'd be saying is that the yield is increasing because the equilibrium would move to the right, where there is a fewer number of molecules or moles of gas, or the fewer particles of gas. The second half then is talking about the increased rate of reaction. So this is where collision theory comes in, and we move away from Le Chatelier's principle. So when we increase the pressure, what we're saying is that there's going to be more collisions every second, or the rate of the reaction is going to be faster. The reason for that is going to be because there'll be more particles compressed into a smaller unit volume. Okay? Kind of similar to when you increase the concentration. Note that when we're looking at this, it does say that there's a rate indication, a time indication, not just that there's more collisions. There will actually be the same number of potentially be the same number of collisions in total. It's just getting there faster, because that's what a rate of reaction means. Right, enough waffle. 9.5. How a catalyst increases the rate of reaction. At least one of you read the revision guide really carefully here. Most people who got the mark for saying that it lowers the activation energy, and hopefully remember the graph where it shows the products and the reactants, and it shows that step-in energy, and then there's the bump, which is the activation energy. Now, when you use a catalyst, it will lower the activation energy, and it works on the principle that for the same thing as when you're calculating bond energies, regardless of how you get from the reactants to the products, the amount of energy change is always going to be the same. So even if you broke apart every single bond that's in the molecule, when you reform it, when you reform it into the new products, it will take the same amount of energy overall as if you only broke a couple of bonds. Now, what a catalyst does is it provides a different pathway. It allows some easier steps along the way, which means it takes less energy. 9.6 then. Just notice it says do not give an answer in terms of increasing the rate of reaction. So why do we use a catalyst? Not talking about time. Again, it links back to that last thing. It provides a lower activation energy, less energy is needed, which means then that lower temperatures, lower costs, and anything else that might well then be linked into that as an explanation. For 9.7, bit of a trick question, apart from when we looked at Le Chatelier's principle, we looked at this. Catalysts speed up the rate of reaction for both of them. You don't get a mark for saying that because the question specifically says what happens to the yield of methanol. There's not going to be a change. The forward reaction will be faster, the backward reaction will be faster, and then the overall concentrations, masses produced, the yield, not going to change at all. Cheeky. Right, number 10. Again, evaluate question. So as Mr. Greenarch likes to waffle on with, on an evaluate question, you are going to make a judgment. Okay? In the case of these 6 mark questions, we're looking again at these, the level 3, it's going to be logical, it's going to be linked to the information that's in the table, and you're going to be using correct reasons. The reason it mentions life cycle assessment is because there's 4 stages to a life cycle assessment. So if you're getting into the top area, you need to mention about the raw materials, the manufacturing, the usage, and the disposal. All of those, not every point in it, but a consideration to each. And if you miss any of those, then you're probably going to drop down into the 3 or 4 marks. So let's look at the raw materials. So the first thing to say is that the wood would be a renewable resource, and that the crude oil would be non-renewable because of where they come from. Wood can be grown, and the polystyrene cups are going to be coming from a finite resource from crude oil. There's other points that you can say in there. We don't need to get too crazy about it though. Let's look next at the manufacturing. So the energy required to produce the paper cups is far more than the polystyrene. It's one of the points that you could say. It's a much bigger number, which is not necessarily great, is it? When we're looking at the usage, both of them are single use. You're going to throw them away regardless. When we're looking at disposal, you might say paper cups are good because they're biodegradable, so that they're not going to, affect turtles and all the other stuff that's on the news at the moment. You might say that the polystyrene cups are better because you can recycle them, which means that you're going to extend the life of a finite resource. Which is now where we come to an evaluation. You make a judgment based on the advantages and disadvantages that you've just given. So overall, I think the best cup might be the polystyrene cup because it's got less mass for transport, takes less energy, and can be recycled at the end of its use. Or maybe you said the wood is better because it's renewable, it can be burnt instead of being thrown away, so it can be used to generate energy afterwards as a biofuel. As long as you're making linking your judgment into what you've talked about, you're doing good. 10.2. The energy needed to produce 1 kilogram of coated paper cups. Cheeky thing here then. Kilogram, and in here they give you the mass of 1 cup in grams, 8.3 grams. Okay, so what information we need from the table? We need to know that 1 cup is 8.3 grams. The energy required to produce 1 cup is 550. Okay, so the sum should look like this. 1,000 comes from converting the grams into kilograms. The 8.3 comes from the mass, and the 550 comes from the energy, which means that you should come out of a number of 6.63 times 10 to the 4. Okay. So several different ways that you can get to the number depending on how you approach the problem, and I don't really care how you do the maths to get towards it. The problem that a lot of people might have come across is neglecting to include one of the particular numbers from the bits of information. 10.3. The clue here is the not melting bit. Okay, so this is when we looked at plastics again, and we looked at two different types of plastics. We had thermosetting and thermosoftening. So even if you don't know what melamine is, there's your clue that when it says it does not melt, that's a thermosetting plastic, and we said that's things like you might find in a kettle. And the reason that that's going to be so difficult to melt is because there are going to be cross links. So we had chains on the picture on the board, and there were solid lines joining them instead of dotted lines. The dotted lines were what we were showing in the thermosoftening plastics. They were the weak intermolecular forces. Now, this one, the cross links, are bonds. They are much stronger. That's why they are solid lines in the diagrams, and that's why it says do not accept a reference to intermolecular forces. These are the cross links are strong bonds. So congratulations for putting up with me talking all this long. I'm finishing this. If you've got any questions, make sure you do ask, because some of those bits do get quite confusing. But well done, guys. I'm proud of you.